Mendel's law of independent assortment states that alleles for separate traits are passed on independently of each other. And with almost all topics in biology, there are exceptions. The inheritance of linked genes, which are genes on the same chromosome located close to each other physically, is the exception for Mendel's second law. While the inheritance of genes on different chromosomes is independent due to the random orientation of chromosomes in metaphase 1 of meiosis, linked genes have a higher than average chance of being inherited together due to a lower chance of homologous recombination when the distance between two genes is small. The degree of genetic linkage is measured by centimorgans, also called map units, in which a 1 centimorgan distance indicates a 1% chance of two linked genes on the same chromosome being inherited separately, aka recombination. However, it is important to note that centimorgans is not a measure of the physical distance between two genes, but rather the probability of recombination. While these two terms are closely related, they are not equivalent. I'm sure we've all seen examples of experiments in which the map units between three linked genes do not add up. The genes furthest apart always have a smaller centimorgan value than the sum of the two centimorgan values between the distal genes and the middle gene due to double crossover events. Let's try to come up with an equation that relates the observed recombination frequency and physical distance. Let's first assume that there is an equal likelihood of crossing over between any two adjacent bases. That is, the rate of crossing over is proportional to the physical distance between bases on a chromosome. Let's also assume that crossover events are independent. And finally, let's assume that there can only be an integer amount of crossover events. By doing so, we can model the probability of crossovers by Poisson distribution, where m equals rd. D represents the distance, r represents the rate of crossing over per unit d, and m represents the average number of crossing over events for distance of d. The small x represents the number of crossover events, and the probability of x crossovers occurring for random variable x is represented by p. So now we have a relationship between d, the physical distance between bases on a chromosome, and p, the probability of x number of crossovers occurring. So how do we establish a relationship between the frequency of observed recombination of two linked genes and their distance d? Say we have a pair of linked autosomal genes A and B, both genes dominant on the maternal chromosome and both genes recessive on the paternal chromosome. If there are 0 crossovers between A and B, the two genes on the same chromosome are inherited together. If there is 1 crossover between A and B, the two genes on the same chromosome are inherited separately. 2 crossovers inherited together. 3 crossovers inherited separately, and so on. Therefore, the probability of recombination for two genes is the sum of the probabilities of all odd numbers of crossovers occurring, and the probability of no recombination for two genes is the sum of the probabilities of all even numbers of crossovers occurring. Since I had no idea how to simplify these equations, with a little magic from Wolfram Alpha, it shows that the infinite sums are the Taylor expansions of the hyperbolic sine and cosine functions. Now, focusing on the first function, we have a function that relates the physical distance on DNA to the probability of recombination. Graphing this function shows that as the distance between two genes on the same chromosome increases, the probability of recombination increases, but plateaus at 0.5, or 50%. This corroborates some of the facts we already know about genetic recombination. Recombined gene pairs very rarely occur at a higher frequency than non-recombined gene pairs. Gene pairs on the same chromosome exhibit patterns of independent assortment if they are far apart. And for multiple genes on the same chromosome, the sum of the recombination frequencies in centimorgan for adjacent genes is always greater than the total recombination frequency in centimorgans measured for the two genes at the ends. Rewriting this equation so that distance becomes a function of recombination probability gives us Haldane's mapping function, perhaps more useful because it is more common to use experimentally observed recombination probabilities to determine physical gene distances. This model is very rudimentary because of one assumption, that there is an equal likelihood of recombination at all locations. I'm not even close to an expert in molecular genetics, but my best guess is that the recombinase enzymes recognize specific DNA sites for crossing over. Therefore, recombination frequency is not entirely distance dependent. Also, epigenetic modifications such as DNA methylation might also change the probability of recombination at certain regions. Both of these issues render the initial assumption invalid. But in any case, this model remains applicable on the macro scale. Thanks for watching, and please point out any mistakes I made or link any related articles in the comments section below.